So welcome you all for this seminar by Professor Mike Wallace. So it is a privilege to actually introduce Mike Wallace because I'm sure most of you have looked at used his book as a reference book for getting introduced to atmospheric sciences and learning, irrespective of your background. So you must have noticed that the book caters to physicists, engineers, geographers, and so on. So ideally, Mike does not require any introductions, but for the sake of completeness, I'll just introduce him. Also, if you have worked on or if you have read about any mid-latitude atmospheric oscillation, you would notice that Mike had some role to play in his discovery. So we are fortunate to have a scientist of this nature today giving a talk to us. His CV is really long. I have already made it short, but even the shorter version is difficult to remember. So I'll maybe read parts of it. He is right now Professor Emeritus in Department of Atmospheric and Oceanic Sciences at the University of Washington in Seattle. He did his PS from Webb Institute of Naval Architecture in 1962, and then PhD from MIT in 1966. His interests are atmospheric general circulation, geophysics, climate variability, meteorology, and so on. He's received several awards. Some of them I'll mention, but there's a long list. Please check his website. It's a CV which we all should pursue. It's a dream CV to have. He's a recipient of Messenger Award, which is given by American Meteorological Society. He got it in 1975. Then Rossby Award, again given by AMS in 1993. He received Weddell Medal, given by EGU in 1999. He was the director of the Joint Institute for the Study of the Atmosphere and Ocean, GISAO, for around 20 years in two different phases. And recently, for past several, I think 10 to 12 years, he's been involved in groundwater arsenic testing and mitigation in Balia district, which is in the Uttar Pradesh. So, in some sense, his experience and work spans a really wide spectrum. Mike has fortunately graciously agreed to be available for personal interactions with students and faculty in the afternoon. So please, if you have some questions, please you can come and on the ground floor of civil engineering conference room and interact with him at 3 o'clock. So with that, maybe put your hands together.
Good. Well, I want to thank you for coming today. I have to say that this is my first lecture since before COVID. It's been more than 3 years since I've been in a place like this. I also happen to have a cold today. It's not COVID. I already had that. But so I'm maybe not at my best, but I'll do my best. And I have plenty of animations, which I think will help keep you awake. My talk is going to cover a 60-year period, as it said in the title, from just about 60 years ago. Right now, I was a graduate student at MIT in Boston, and I was introduced to the topic of the atmospheric general circulation by the faculty there. And I had a lot of interaction with Victor Starr, who was one of the leaders in that area. And so I'm reflecting on my own experience as I began to learn this subject, which really has a lot in common with atmospheric dynamics and synoptic meteorology. And in some ways, I think that over the years has if you think in terms of the globe, it maybe has replaced those as a single theme that embodies the part of meteorology that is observational but connects with the theoretical as well, and is closely related to the use of models. So I just wanted to start with a few thoughts of how things are different now from 1962. First of all, obviously, the computational speed and data storage. You can, with the data you can store on your phone now is, I think, about as big as the U.S. National Weather Records Center, which I visited when I was a graduate student, and it occupied the whole building of a hotel. All of the rooms were full of data, and it was like one city block. And now that's about equivalent to what's on your computer. Another thing that has changed is when I was a graduate student, I saw the very first satellite pictures of the atmosphere, looking down, seeing very crude images. They were like images on television, seeing clouds with visible imagery just from space for the first time. And now the data from satellites, both the imagery and the digital data for like the temperature field and relative humidity field, and in some cases even the wind field from some parts of the atmosphere, have just revolutionized the data. Back when I was a graduate student, people were analyzing maps by hand and using these data at widely spaced grid points, and now we have the resources to handle huge amounts of them. And not only the in situ data, but the satellite data as well. And then I wanted to mention the reanalysis, which I think many of you are already familiar with. The idea of that in place of the hand analysis that we were doing at that time, drawing lines on maps, first came objective analysis. The people taught the computer to do interpolation algorithms just for one variable at a time, a map for zonal wind, a map for meridional wind, etc. And then to go to multivariate analysis, first maybe putting together the two components of the wind to have a single vector field, but it was not long before putting together wind and temperature, first using the constraint of just the geostrophic equation, the thermal wind equation, and then later using the full equations of motion and using the forecast from a numerical weather prediction model as the first guess for the reanalysis, for the analysis, the operational analysis, and using the data that was just coming in, the real-time data, to correct the first guess, to correct the errors in the model forecast, bringing it closer to reality. So that technology has developed very rapidly, and now the state-of-the-art reanalyses, like some of the ones I'm going to show today, have resolution down to about 1/4 of a degree of latitude, a little bit less than 30 kilometer resolution between grid points. And also, it has hourly resolution rather than resolution of once or twice a day, as it was back at that time. Let's see if I can back. Oops. I want to go to Oh, oh, this, that'll go away, I think. No, I can get out of, whoops. Are we back? Yes. Maybe I need to be moving this more aggressively. So I'll just mention also, we have some very good visualization tools, the color imagery, false color, and animations. And so I'm going to be showing you some of that today. So that's just in way of introduction. And so just as background, I'm going to, I have one slide about just the theory that underlies all of atmospheric dynamics, that we are solving the Navier-Stokes equations, all of our governing equations for numerical weather prediction, climate prediction. They're based on the Navier-Stokes equation, and those equations allow for three different kinds of waves: Rossby waves, gravity waves, and acoustic waves. And they're arranged here in order of from low frequency, slowly evolving waves, to faster. Gravity waves are much faster, and then the acoustic waves much faster than that. And so we have now, with today's reanalysis products with hourly resolution, we're going into the realm where we can actually see gravity waves as well as Rossby waves. Not all of them, because there are gravity waves with scales smaller than we can resolve, frequencies higher than we can resolve, but we're getting a lot of them, and that makes the analyses a lot more interesting dynamically. So just wanted to show you, this is a picture from our, like the cover of our book that's going to be coming out in a few months on the general circulation, and a picture of I think this is the MODIS satellite imagery extending over the whole world. And when you see a picture like this, you are impressed with the Rossby waves. We see like a train of vortices marching across middle latitudes in both hemispheres, and these are the baroclinic waves, and their behavior is well described just by equations treating them as Rossby waves. The other thing we see, it's not so clear in this picture, but if we blow up, just zoom in on the tropics, we see deep convection. Actually, we see shallow convection if you look in the trade wind belt. You'll see little gray patches. So we do see convection, but in these images, we don't see anything that looks very much like gravity waves. And even when we do animations, we can see these baroclinic waves evolving, moving along, going through their life cycles. But the impression of animations like these is that it's very slow, very low frequency. It's evolving from day to day. We don't see anything hour to hour, except with the convection. So the gravity waves seem to be missing. So much of my talk today is going to be about gravity waves, because this is one of the new things. One of my talk is about the evolution of the field, and I think we're just moving into a new phase where we have a more complete solution of the Navier-Stokes equations, and we're seeing more, which means that we can see phenomena that we could not see, not even dream of seeing when I was a graduate student. So gravity waves are really important in the general circulation, and there are two main ways by which they're excited, by deep convection and by orography, by mountains, flow over the mountains that induces waves. They play a very important role in coupling the deep convection that you could see in those images I just showed with the large scale motion. So coupling the fluid motions across scales from the convection, which is just on scales of kilometers for the deep convection, to the scales of even planetary scales, even 3 orders of magnitude greater. So, and I'm going to show you an example of how that happens today. And finally, then a whole separate class of waves associated with orography, with mountains, and they turn out to be very important because they convey the effects of frictional drag in the boundary layer to the whole atmosphere, even and especially the upper atmosphere, the upper stratosphere and mesosphere and thermosphere. And so those pressure gradients across the mountain ranges, even on scales of 10 kilometers, produce waves which break in the upper atmosphere, and where they break, they slow the zonal winds down. And if we had a period in the 1980s when the general circulation models seemed to be getting worse each year. As more resolution was added, it seemed like the jet stream was getting out of control. The westerlies were getting stronger and stronger with every model, and they were quite unrealistic. And it took a few years to realize that the problem was that the increasing resolution was making the westerlies stronger, but there was no compensation from the gravity waves induced by the mountains. So it wasn't until they put in, they had to be parameterized, the gravity waves, that brought the westerlies under control, and they started to get realistic circulations again. So with that, I'm going to show you some gravity waves. And this is a picture, I think you might recognize Japan here, and with some of their script. And this is dates. This is the 15th of January, 2021. And maybe you don't remember what happened on this day, but when I show you the animation, I think you'll get an idea. And the windows. Oh, okay. So I'll show you that again. This, I should say, we're looking at sea level pressure. This is a network of sea level pressure, and the red band is a sudden rise in sea level pressure, and then that's followed by a dip. So it goes above and then below, and then it comes back. And this is a wave coming from the southeast going to the northwest, and it's traveling at the speed of sound. And so it passed over Japan in a matter of less than an hour, I'm sure. The same wave passed over Seattle, and I don't know if it's true or not, but it said in the newspapers that the clouds, which are almost always there in Seattle, in my home city, that they dissipated for a few minutes when the wave went past. So to give a more global view of that, this is satellite imagery that has been processed to emphasize the very highest frequencies by taking successive images and subtracting them. It's like a very strong high-pass filter in time. And this is, oh, I should say this is looking down on the Pacific. And the Americas are over on this corner here. Japan is over here. Let me do this again and look down in, look here. You see a ring, and if you look very carefully, you will see, I have to play this several times, from this spot, you will see that there is one ring that goes very fast, and it goes all the way to the edge of the image during this time. And then there are other waves that are expanding much more slowly. I'm just barely, raise your hand if you see the fast one. So a lot of you are, right. So that is what you saw in the image of Japan. It was the fast one. The slow ones never got there. They don't travel that far. And just to summarize what's going to be coming later, the fast one is what we call an external gravity wave, and the slow ones are internal gravity waves. So here is, think of this as just a frame from that animation. On the left, the satellite image with a little more processing, and so the ring shows up a little more clearly than it did in the animation. And on the right, it's a shallow water wave equation model, and this is work done by Nadia Zagar. And these, I think these images appeared in an article in Nature about the eruption. And here is another rendition by the same, there's a Matthew Barlow who made these images. The same man made this one, but this one is just rendered in black and white, and you can see the two kinds of waves very clearly. You know, the fast one is gone in just a little bit, and then the slow ones follow. There is a little bit of mixing between the fast and the slow in this image, and I think that's the filtering. I think that's artificial. They really are two different phenomena, the external and the internal. So that's what gravity waves look like, at least in the satellite images. And now I'm going to try to argue that some of these waves are obviously some of the gravity waves, and I'm talking now from here on mainly about the slow ones, are forced by convection, especially tropical convection. So we're going to go back to that same Tonga eruption of the volcano in the South Sea Islands, and this is visible imagery, and the colors are showing us the deepest convection and the coldest temperatures, which are an indication of cloud top temperatures. The red are the reds, and they're the places where the clouds extend all the way up to the cold point tropopause, very cold tops. So they are the deepest convection. And in this, you're also going to see the Tonga eruption. It's going to show up over here. But I want you to notice that that's not the only show in town, as we say. So there it goes. And you see the external gravity wave lasted only a second. And look at this wave over, or this convective cell over here. This was, this one has nothing to do with the Tonga eruption. It was there before the eruption started, and it lasted till afterwards. And let's go back to this one, and you can see that other cell in this picture. Look to the east of the big one. Let's see. Oh, here it is, right there. You see just continuous emanation of slow waves from this point. So it's not only eruptions like Tonga that emit gravity waves, convection does that too. And so I want to show you an image or a still picture that one of our graduate students, Hamid Pavlovan from Iran, constructed. And this is based on ERA, the European Center Reanalysis 5, the latest, the state-of-the-art product, the hourly fields. And it's a composite, and the reference variable for the composite is sea level pressure, the same field that we looked at in the surface stations over Japan. So the key thing, the composite is keyed to pressure jumps, pulses of high pressure, and it's filtered so it's very short-lived high pulses that are there for 1 hour, but not there the hour before or the hour afterwards. And then we're looking at the same variable, sea level pressure, 2 hours later, 4 hours later, 6 hours later. And then this is for points all along a latitude circle, and I think this was actually along the equator. I think it is like grid points at 1 degree apart, so as to have a very big sample size, 360 grid points, and we've got data for 10 years every hour. So there are millions of members of this composite. And just for graphical purposes, the reference grid point is placed on the location of Krakatoa here, and by 2 hours later, we're seeing what looks like a train of waves going out from this synthetic eruption of Krakatoa, which is really just pressure pulses, not in 1886, but in like 2015 and the last decade. And so it looks like here, like it's a train of waves, but again, this is the high pass filter that makes the rings. If we had perfect data here, this would be just a ring, just a single ring like we just saw. And here it is a little bit later. Oh, it just keeps coming out. Okay, so here it is, 4 hours, 8 hours. By this time, it's going over the horizon. It's gone halfway, let's say a quarter of the way around the world. And so we switch the projection here, and we center it on the antipodal point here, which is actually this one. This is in Panama. This is the Krakatoa is 6 south, this is 6 north. And we see the wave sort of coming over the horizon and converging on the antipodal point and getting to the antipodal point in 20 hours. And then it takes another 20 hours to get back to Krakatoa again. And this is the same kind of sort of 40-hour period that G.I. Taylor published papers on studies of back 100 years ago, based on Krakatoa, and this is based on real data on pressure pulses. Or I should say, that was real too. This is based on current data. This spot here is due to the incomplete removal of the diurnal tide. It's not a physical thing. So the point of showing this figure is to show that using pressure pulses, and they are, I'm going to argue that they are associated with convection. This gives us external gravity waves, like the one from the Tonga eruption. It also gives us internal waves. And I want to show you now, this is satellite imagery, cloud top temperature in a tropical cyclone. And you're going to see this as an animation. And you will see gravity waves emanating out from the cyclone. You see the rings radiating outward very rapidly. Oops, I have to show you this part, which is just, don't pay any attention to. How many of you saw the rings in the colored part? Did everybody see them? Yes. Would you like to see that again one more time? Yeah. So just continuously emanating.
So Mike,
yes.
When you say external, is it?
Oh, these are internal.
Yeah.
These are the slow ones.
Correct. So both external, internal are with respect to the tropopause, or is it going through?
With respect to the tropopause. That's meaningful, I think, only for the internal.
Right.
So this is for the depth of the tropopause, and we'll see some evidence of that later on. Okay. So this is a picture, just an instantaneous picture of the vertical velocity field. And it turns out, I think this one is for up in the stratosphere at 50 hectopascals, around the 20-kilometer level. But we looked, the 500 millibar vertical velocity field looks just like this. And this is a picture at the same time, satellite imagery showing the clouds. And you can see from each of these tropical cyclones, there are rings emanating on a day-to-day basis. And you can make animations of this. It's a little bit jumpy because it's hourly resolution, but you can see any kind of cyclone. It doesn't even have to be an intense one, will be a source of these waves that will be radiating out. Okay? And it doesn't have to be an organized storm like a tropical cyclone. I'll show you a couple of examples. Here's an animation over Australia. This is a very popular one that is on a couple of YouTubes. Watch this image and you're seeing it for a day and a half, day and night and day again. This is night again, and you see it. And now there's another ring from convection, and this is convection over northwest Australia in their monsoon season. I'll play that again one more time. And you notice how it is just a very narrow band of waves, but they are waves. You see multiple cloud bands. So these are traveling at about 50 meters per second or so is and that is the phase speed of what Raghu mentioned, the sort of the gravest internal mode, the internal mode with a depth of the whole troposphere. I'm not going to show it here, but there's very clear evidence of a second mode too that travels at about half that speed, at about 25 meters per second.
In terms of the vertical propagation, which one is the most important for stratospheric?
If you're interested in phenomena in the stratosphere, you have to be concerned with both. Like, for example, the QBO with wind speeds in the 20s of meters per second, it feels these second modes, basically. Namely, the first mode is too fast. I can show you some other, there are other images in the book where you can see the vertical propagation. I don't have any in this talk. Okay, and just another example. This is just a kind of a random arrangement of convection over the western Great Plains of the United States, and you see these gravity waves emanating out from it. So the message is that gravity waves are an important source of convection. And here is another one of these composites. And this time, the reference for the composites is not sea level pressure, as in the other one. It's what we call a downwelling event in the tropospheric vertical velocity, the mean vertical velocity of the whole troposphere. If we take the time series of that and we look for the strongest subsidence, it turns out. Subsidence gives a better signal than ascent. And so if we take those events and we make a map, and the maps are of the thickness of the tropospheric geopotential height field. That's a measure of tropospheric temperature, the temperature of the whole troposphere. And you see that it's warm. It's like a warm expanding ring. And we stop after 8 hours, but you can actually follow this for 16 hours in the composites. That's because we have something like 1 million events in this. Okay, and probably not all of you will appreciate these next two plots, but these are spectra, and it's quite a common way of representing waves in the literature on the stratospheric dynamics is to use these so-called two-sided wave number frequency spectra. George Wallace in the United States, I think, has pioneered this area as much as any. So the vertical axis here is frequency, and of course that's the inverse of period. So we see frequency increasing as we go up. So down at the bottom we're seeing waves with, at this level, periods of 5 days, 2 days. Here's the diurnal cycle, the semi-diurnal 6-hour period, and the highest that we can resolve, the highest period that we can resolve with hourly data is a period of 2 hours, and that's at the top. And then the x-axis is zonal wave number, and you see it goes all the way from 0, zonally average, to wave number 1, one wave all the way around a latitude circle. To the smallest scales, it's 360 waves along the latitude circle. So the variable that's plotted here is the co-spectrum between geopotential height at the surface at the 1,000 millibar level and at the 200 millibar level. So it's a measure of the it encompasses the whole troposphere, roughly. So what you see, so this is calculated based on the ERA 5 data, based on the last 10 years or so. And the red curves are theoretical curves. They're the dispersion diagram, very much like the ones in Matsuno's paper back in 1966. But this has been adapted to the whole globe. Instead, it's not the equatorial beta plane. This is spherical. And this is also used in tidal theory, this set of curves. And you see 3 families of curves. This one over here, the one labeled Rossby waves, all by itself. This is the well-known wave number 1 and 2 Rossby wave with periods around 5 days. This was detected back in the 70s and 80s. This is a Kelvin wave with a period of about a day and a half. There are also papers about this. And there's a Kelvin wave for every zonal wave number. This is 1, and then there's 1 for zonal wave number 2, 3, the whole line of them. And then there's this whole group up here. This is the internal, I should say, inertial gravity waves, IG waves. And so all of these waves show up as external modes, and they show up as orange, which means a positive. There's a positive co-spectrum. There are the peaks in positive peaks in the co-spectrum. That's where the height at the 2 levels is in phase. So external waves are in phase in the pressure field at all levels, all the way up to the top of the atmosphere. So they can only be orange. But you see these bands of blue, and they are continuous. They're not discrete zonal wave numbers. And blue is negative. That's where the geopotential at 200 and 500, 200 and 1,000 top and bottom of the troposphere are out of phase. So these are waves in the tropospheric temperature field. They're waves in the thickness field, and they're the waves we're just looking at. They're the internal waves, and so they have slower phase speeds and we go slower. This is the fastest one. Infinite is right on this axis, and the speeds get slower as we go out. And so they're out at 50 meters per second. And actually, if you look at this, you can see here, and if you blow it up, you can see over here too. You can get a hint of the next mode, which is positive. So, okay. So now I'm going to switch the topic completely to go away from tropical convection, and I want to just show you a few slides that are showing orographically forced waves. And the first one, actually, I'm going to go back to the Tonga eruption, and we're going to look. We're going to look at that, a zoomed-in version of the one I just showed you, and this is the eruption itself. So let's look at that again. And this is in the visible window, so we're seeing the cloud top temperature. And this is the ash cloud as it expands, and towards the end begins to settle down after getting up all the way to the stratopause, all the way to 50 kilometers. As we go from greens and back into the reds, it's getting colder, and it means a lower cloud top. We're getting down, the cloud tops are only around the tropopause at the end. You see again, the external mode just exploding out very slowly. But if you focus on this feature here, you see there are waves that are hardly moving at all. And this is just the ambient winds at this level being blocked by the cloud and the rough edges of the cloud and forming lines of gravity waves along the edge of the cloud that more or less sit still. So it's another family of gravity waves with almost zero phase speed. So here's another example. This is over England, and we see there are weak westerlies here, and we see clouds going from west to east. But you see those bands of dark and light color that are just stationary. They're anchored to the little mountain ranges there, and they have scales of like maybe 10 kilometers or less. So, and this kind of wave is everywhere. It's just that we don't always see it. There are a lot of cloud photos, just visible images that show these kind of waves. Okay, and and here, just to show that these waves affect the general circulation, we'll go back and I'm going to show you two images here based on the reanalysis data, the ERA5, and this is the wintertime, December, January, February, vertical velocity field at the 500 millibar level. It's just the climatology of vertical velocity. And we see this yellow ring here. That's subsidence. That's a sinking branch of the Hadley cell, is that ring. And we see that there's a lot of fine structure here that's on the scale of the mountain ranges. And if you have a topographic map, you'll see that these banded structures here line up with the finer mountain ranges. And we see a blow up. This is the same image, but I've just zoomed in on this longitude and I rotated it so that India is on the bottom. I guess this is Bombay right here, is that right? And so here are the Himalayas. And we see a band of ascent here and then general descent over this whole area of northern India. And this is a winter image, and this fits the pattern of the fog. And we see the clear band, and I think that corresponds to the ascent we looked at. And then the broader band, this is fog, and then you can see aerosols out here. This is just a day in January, and that region of subsidence, that's what creates the inversion that holds the aerosols down in the boundary layer, and when the air gets to saturation, we get the fog forming. It'd be very interesting to make a map like this based on a composite of fog days. I think that'd be an easy little classroom project to do. This is the simplest kind of composite. You're just averaging the data together on a set of days. So I'm getting close to the end here, and I have just one sort of big picture slide taking us back to the notion of the general circulation and the idea of the three different kinds of waves. And in this case, it's a spectrum, but it's just one-dimensional spectrum of zonal wave number on this scale. So we go from zonal wave number one wave per all the way around the latitude circle, and highest we go is 100 waves around the latitude circle. That is a conservative place to stop with this spectrum, even though we have data with a resolution of a quarter degree. You might think we could go out to almost 1,000 here, but computationally, if you want to be sure you've resolved the waves well, that conservatively it's a good idea to stop around 100. And so the whole spectrum is the black curve, which follows along here and then along here. And these reference lines here are from theory, and the -3 curve, which fits the total, and it fits the Rossby wave part very well, is for turbulence which is constrained to be two-dimensional. And in the atmosphere, Joel Charney showed one of his many contributions that because of the geostrophic constraint, that the horizontal motions in the atmosphere tend to be two-dimensional, that the vertical velocity is smaller than it would be in just classical three-dimensional turbulence. And so under those conditions, we get the -3 power law, fits the data. But if we look here, we start off at the biggest scales, you can see that it's broken up into Rossby waves and inertial gravity waves, and the out at this range of wavelengths, it's all Rossby waves, and the energy in the internal gravity waves is more than an order of magnitude less, and so it hardly contributes at all. And so this is sort of the view that we had of the general circulation when I was in graduate school, that it's all about Rossby waves. Here's the scale of baroclinic waves, and we get to the other side there, and even here, it's predominantly Rossby waves, it's almost all. But then, when we keep going, and now we're getting into the realm of the modern reanalyses, where we have the much higher resolution, we see that now there starts to be a gap, and the inertial gravity waves are starting to have a substantial contribution. And when we get to about wave number 50, they're equal, 50-50 contribution. And for this last part of the spectrum, it's mainly gravity waves. They're more important than the Rossby waves. This range around here corresponds to what we refer to as the Rossby radius of deformation. And so in fact, if we integrate the over wave number here and just say how much of the kinetic energy of the general circulation is due to Rossby waves and how much is due to gravity waves, it turns out that it's about, I think it's 91% for Rossby waves, because there's a lot of energy in these big scales. But there's 9% for gravity waves. That's not, it's a non-trivial contribution. And then, of course, the acoustic waves are not really resolved here. To get into the acoustic waves, we'd have to go another order of magnitude or two out in this, along the spectrum here. And I haven't even thought out just what we need to do to see them. But I think this may be a challenge. Maybe when some of you are talking 60 years from now, you'll have the story of that. So I'm going to end with just showing you a picture that goes back to my PhD thesis when I was at MIT. and it was about the quasi-biennial oscillation in the equatorial stratosphere. At that time, it was called the 26-month oscillation. It had just been discovered in fact, the foundational paper on that was discovered, I guess, 2 years before I went to MIT. And here is a modern version of it in the ERA5 reanalysis. So we're seeing latitude from pole to pole here, and right in the middle is the equator. And we're seeing height, and we're going from the Earth's surface up to the stratopause, up to 50 kilometers here. And the color is zonal wind, zonally average zonal wind, but it could just as well be zonal wind at a grid point because the waves are only a small part of the kinetic energy up for this. And the orange are westerlies, the blue are easterlies, and they're the departure from the climatology. So we're not seeing the tropospheric jet stream, that's been taken out. We're seeing the variability about the seasonally varying mean. Here we go, and this runs for a while. And why don't you just watch it, and I'm not going to say anything about it for a minute or two here. Compare what's going on in the tropics versus high latitudes. And you might notice that at high latitudes, there's a lot more going on in the northern hemisphere than in the southern hemisphere. Now, how many of you think you can see the QBO? No. Just watch these regimes on the equator. They're about 30 degrees wide. Can you see a tendency for vertical propagation? So, which way are they going? Upward or downward? Downward, right? I can just take this one. I'm leaving the cursor as it was. You see the orange going down, the next blue one coming by the cursor, pretty soon the next orange one. And it takes about a little over 2 years to go from a orange, blue, orange, or blue, orange, blue. So this is a very clean example of a phenomenon that has little, if anything, to do with Rossby waves. It turns out that this, the QBO is forced almost entirely by inertial gravity waves, and including Kelvin waves. And you have to use the shallow water equations in order to get it. You could not get it in terms of the vorticity equation, the equations that we use to study Rossby waves. So here's a phenomenon that is a really first order importance in the atmosphere, and it's pure gravity waves. And I guess that also shows that what goes around comes around. The QBO was the start of my career, and just wrote a couple of papers with Hamid Pavlovan with some of these results relating it to gravity waves. So I think I'll stop there, and the time, I haven't been paying attention to the clock, so I hope we're okay. Good.
Thanks a lot. lot, Mike. We have time for questions, so make sure that you ask questions about the presentation now. And if you have questions in general about science or how we shape this career, maybe reserve them for afternoon session. So questions about the seminar. Yeah. Yes.
Okay, anyway, I can explain.
I should have kept this open, sure. Oh,
Can you go to the frequency wave number plot where you should?
right, and let's see, we have several of those, but,
No, not the energy one, the
Elias.
first one.
this, one of these,
It's not showing.
uh,
I think he's referring to Wheeler and Pilates
uh,
frequency.
This one.
yes, they, those, Wheeler and,
The previous slide.
The one before, yeah, just the slide before.
oh, yes,
Slide number 9.
yes.
Yes, my question was why is the westward propagating mode more dominant in this, in the inertial gravity wave?
In the inertial gravity waves, you mean, why are these,
Why is it not symmetric?
this is a symmetric, I took, in creating this, I took this one, which has symmetric and anti-symmetric, and I just took this one, and I expanded it, and I put some labels on it. So you should think of this as a pair. Here we're seeing Kelvin waves that are symmetric. Here we're seeing the mixed Rossby gravity wave is this one.
Are you referring to east-west asymmetry or probably not hemispheric, but he's saying the peaks in inertial gravity waves all lie in the westward region.
Yes.
Why is that?
Yes, and that is a characteristic of that comes out of the theory. I don't know whether Raghu would know. It has nothing to do with the winds in the atmosphere, because these curves are for a resting atmosphere, and the data fit them pretty well because the external modes go so fast. The only place you have any problems is down here where the Rossby waves are not so fast. So it's an inherent feature of the theory. And I had that same question when I looked at these, and I've asked colleagues, and I've seen these plots in other papers, and I find it not so easy to understand, frankly.
Is it also partly because this is global, right?
This, the data in this are tropical. They're 30 north to 30 south, but the curves are global.
Isn't it more symmetric towards the tropics?
When you get towards the tropics, it tends to wash out the features associated with baroclinic waves. We don't see those features in this plot for these particular variables, but in some of the other plots. Yeah, it does make, there are some interesting differences. Depending on whether you do this analysis for the whole globe, for the tropics, and even just for 10 north to 10 south. And Hamid has done that. But they're not radically different. They're recognizably similar. It's just the emphasis changes a little bit from one to the other.
Also, I wonder if they interact with the mean flow in any way.
No, this is on the resting.
This is resting, and the things all of the peaks here are really fast. They're too fast for the QBO. The QBO is interested in the things way out here. Those are the phase speeds that correspond to the QBO. And I don't have the slides in here, but in fact, these kinds of wave number frequency plots that give you they confirm the theoretical ideas of Holton and Lindzen about the QBO, the zonal wind interacting with the waves to produce this downward propagation.
Any other question? In the meantime, maybe I'll ask. So you showed the second last slide.
Mhm.
You showed zonal wave number versus energy spectra,
Yes.
and this is kind of illuminating that the blue overtakes red.
Yes.
In the
That's why we decided to put this in the book.
Ah.
Uh,
Yeah. So I was wondering if you have a corresponding one for in the time domain. So frequency versus energy.
we don't. That certainly could be done.
Because
And
I
it
was
would be
just I was just thinking from weather point of view.
Yes.
So to answer question about where should we stop bothering about gravity waves in terms of weather and where should we start worrying about them?
Right. I suspect there would be a similar transition here, and it probably would be in the range of a few hours period. And so when you got to the hourly data, it would be mostly gravity waves.
So a few hours, you think tens of hours or only?
No, I
single-
think just single digits.
Okay.
Yeah, I would guess that when you're dealing with the highest frequencies resolvable in hourly data, you're looking mostly at gravity waves.
So in some sense, for weather forecast, we should be worried about them. They could have some predictability too, I guess.
I think, yes, even though you're not concerned about them for their own sake, you're not concerned about the hour-to-hour variability, you are going to get a more faithful representation of the slower modes by including the faster ones with which they interact. In the early weather forecasting, when they were initializing the model, getting the initial conditions from which the model was run, they filtered the data dynamically to remove the fast modes because they didn't feel they could represent them. They thought it'd be better to have nothing than to have erroneous data for the gravity waves. But now it isn't necessary to do that anymore because there is some skill in the analysis on the hour-to-hour time scale. And I didn't show this, but there are a lot of hourly and even faster, higher frequency than hourly surface data that are going into the reanalysis, mainly sea level pressure.
So I guess
There's even talk about, well, in fact, some experimentation with cell phone networks, people having pressure sensors on their cell phones and having them automatically.
Was it a paper from Israel? This one,
Oh.
looking at pressure sensors and from the mobile and looking at patterns.
I haven't done anything with that, but one of the students in our department working with Cliff Mass has a paper on that, and they've been trying to eliminate the biases in. Apparently there are some technical issues with using those data, but it seems like they may be solvable.
Thanks. Yeah, so I saw a couple of times. Yeah.
I still don't understand why do we classify them as internal and external waves of.
Yeah, well, I guess my understanding of that, the clearest way that I think about it is in terms of the shallow water wave equations. If you represent, say, the fluid just by a fluid with constant density and a free surface at the top, that representation can only support the external modes. So it's like the undulations in the free surface in that fluid. You see the internal modes if you allow for like a Boussinesq fluid, where you have a temperature and you can have the density vary as well with temperature. So these modes that involve temperature are inherently, they have to be internal. Whereas those that you're seeing only in the pressure field alone are external.
You think of them as biotropic and biophilic.
Yes.
So the more used.
Yeah, and that is often used.
Maybe Raghu and then Karthik.
Yeah, so I mean, you mentioned horizontal resolutions getting down to quarter degree now,
Right.
and we are still worried about tropospheric, stratospheric coupling and the biases in the models. So in terms of, validating the models by at least frequencies and speed will be quite a challenge as well, just in terms of having data. And so where do you think we are in terms of vertical resolutions in the models for capturing these accurately?
Well, I guess I'm hopeful that even if we don't have the data to initialize the models to get the phases and amplitudes of these very highest frequencies correct, they are, in a sense, figments of the model's imagination. But if the equations are formulated properly, it would seem like the models ought to create something that is quite dynamically realistic, and by having that, it should make the representation of the larger scales, lower frequencies, better. And so I would think that we might be able to validate it, not by comparing it with observations, but by showing that representing, by putting this in, we're getting a better representation of the things that we can measure.
So there is an implied low frequency rectification.
Yes,
And so,
and we see that in a very simple way in the QBO, but I think it's there in everything.
so in terms of the focus problem, then it will become important. If you want to go down to an hourly scale, then you have to get that rectification.
Right. Now, with the orographic waves, they are very small in scale, in horizontal scale, but low frequency in terms of the time domain, because they're very slow moving. But whereas the convective ones have they're very high frequency. So it's a really interesting problem, and interesting dynamically, just on the theory side, and it's interesting from the point of view of an observational person, how to represent, how to think of ways of doing diagnostics that makes them come out clearly in the data. Because you can't see them, as I showed you, you can't just see them in the satellite imagery. You have to do things to the data to make them come out.
Yeah, also the orographic waves are being generated at almost a fixed location.
Yeah.
Whereas the convection is a moving source.
And with both the orographic and the convective waves, the forcing is on, goes down to scales almost just a kilometer or so. So we're still more than 2 orders of magnitude away from actually resolving the real forcing of them. And these composites that I showed you for for example, the downdraft events, those are not on the scale of convective downdrafts. Those are on the scale of clusters of cumulus, deep cumulus, where it just makes the whole region warm.
Karthik.
Thank you for a very fascinating talk. It's probably like almost like a follow-up question. So if you take these internal gravity waves because of convection, so how can we attribute the changes in the weather patterns at any particular location because of these internal gravity waves? I mean, there can be multiple convection activities that
Mhm.
can propagate and which can fluctuate the weather pattern. So,
Mhm.
how can we attribute, or what would be the magnitude of this particular effect on the location?
Well, one way to at least show that it's important is if we consider a volcanic eruption. Could I put this on again? And I just want to show one photo. If I can see it. Oh. So here, I just passed it. So this is a photo taken from space of a volcano erupting. I think it was in the Aleutian Islands, and this is I've seen other photos like this where just here. Well, here is the ash cloud going up, and there's this ring of clear sky that is dissipating a cloud deck that was here before. Well, this is subsidence warming that is warming and drying the air and getting rid of the stratus clouds. And so that ring is expanding at 50 meters per second, like this is an internal mode. This is not the external mode that we're seeing. And so the heat released in the eruption is being spread to the region around it. And so think of this as an allegory for cumulus convection. You have latent heat released in the updraft of the deep convective cloud. It's these waves that convey that heat so that you're making the whole region warm. And that's what makes, that's why you have tropical cyclones, because the whole region warms up. Those gravity waves are spreading the heat. So the orographic, I think it's maybe a little different interpretation, because that has a lot to do with the drag when the waves break, and it's a little more complicated.
So if you consider a particular location, and if you try to monitor the weather in that location, so there can be effect of these waves from
That's right. The waves are coming from everywhere. You get the impression from pictures like this that it's very local, just rings, but it is a kind of a statistical distribution of these rings.
Yeah, we have one question.
You showed the composite of 500 HPA vertical velocity, I think in slide
Yes.
number 24, in the winter on the Himalayan region.
Yes.
So what happens in summer? Like, it might be trivial, but you don't see such strong differences in vertical velocity in summer.
Yes, we made this figure only a few months ago, and there was this same Iranian graduate student, Hamid Pahlavan, who was very busy getting his thesis done, and I didn't feel I could ask him what does summer look like. But that's something any of you could easily do if you have these data, even a part of the data on your server. This is a very easy calculation.
I have actually looked at summer, we don't see that pattern. It must be something related to when the monsoon is strong, maybe we don't see these waves are being suppressed somehow.
Right.
I'm not sure why, but
Right, I think that it's interesting, first step is doing it by season, but then the next step is doing it within one season, like summer, and doing it on at times when the monsoon is strong, say over North India or South India, so composites based on the synoptic situation. And likewise, I think in winter, it would be very interesting to take fog versus non-fog cases and see what it looks like. Yes?
So I have a question as a follow-up to the weather answer. So in Himalayas, at a place in Himachal, so apple crop gets damaged by hails. So as a way around, there's a proposed solution called a hail gun, by which they shoot it from the surface, and the theory is that the gravity waves thus generated will disperse the vertical updrafts, strong updrafts, which cause hailstorms, and it will just lead to some liquid precipitation. So I'm not sure if it is. I just wanted to ask you whether it's true, whether gravity waves could just kill those vertical updrafts.
I wish I could answer that, but I don't have any strong idea. Just intuitively, it seems it would be remarkable if it did. Ideas like this sound to me a little bit like, very creative and interesting, but almost like science fiction. But I can't say that with any conviction.
Because they are being used a lot now,
Mhm.
and I don't know if they've been tested, but
Right. Well, cloud seeding is also being used a lot now in other places, and there's no evidence that it works at all. In fact, I think India is one of the places where there's a lot of it.
And the energy in convection probably would be an order of magnitude more than.
I would think so. Yeah, these gravity waves, when I'm emphasizing that they're important, and I just want to say they're significant, I'm not saying that they're hugely powerful.
Are there any more questions? But you always have kind of time to interact with him in the afternoon. So maybe shall we close then the session? Yeah, let's.
But I'm glad we were able to. I'm fine. Yeah, I just, it's my group.